Good morning. Welcome to the Jasmine Ballroom. We have a journey from JNDI LDAP manipulation to remote code execution dreamland. Before we begin, I've got a few notes for you. Stop by the business hall located in Bayside A-B during the day for welcome reception at 1730 to 1900 tonight. The Black Hat Arsenal is in the Palm Foyer on level 3. And join us for the Pony Awards in Mandalay Bay, B, C, and D at 1830. And thank you all for putting your phone on vibrate. Your ringtone is not as cool as either of these twos. Thanks, guys.
OK, thank you. So welcome to our talk. And our names are, well, my name is Álvaro Muñoz. I'm Principal Security Researcher with HP 45. I'm known as Pwn Tester in Twitter and IRC. And here with me, my colleague, Alexander Miros, that is Senior QA Engineer also with the HP 45 team. So we have a brief but packed agenda for today. We're going to introduce, first of all, the basic concepts around JNDI, the Java Naming and Directory Interface. That is going to be the foundation for two new types of vulnerabilities that we are presenting today. The first one being JNDI injection, and the second one being LDAP entry poisoning. So we will be presenting different vectors for exploiting these vulnerabilities and also some demos on real-world application to show you how they look like in the real world. So last year, the NATO and the White House were hacked or attacked as part of the Pwn Storm operation. And this operation basically used a bunch of 0 days, and among them, they used a 0 day to bypass the Oracle Java applet click-to-play protection. So basically, they were able to serve a malicious website that when these NATO and White House employees visited these sites, they were able to trigger the execution of the Java applet without the employees having to explicitly click in on the applet. So for that, they used several tricks and several exploitation techniques, and one of them was some JNDI features that we found very interesting. And so we decided to research on this JNDI technology and see what we could get with them. So first of all, we are going to introduce a very brief introduction to JNDI, enough so that you can understand the basics of these vulnerabilities. So JNDI stands for Java Naming and Directory Interface, and it's basically a common interface to interact with different naming and directory providers. So naming provider, naming service is basically a system that binds a name to a given value or a given object, right? So you're probably familiar with naming services like DNS, where we bind the IP addresses to the host names, or for example, with a file system that binds the file name to the file itself. So directory services is a special type of naming service where we are basically binding a special type of object that is known as a directory object. And directory object is nothing else than a collection of attributes. So you're probably familiar with LDAP as an implementation of a directory service. And in LDAP, normally we store things like the employee records with all the collection of attributes, like what's the name of the employee, what's the email address, the last name, the first name, and so on. So the JNDI architecture is very simple. It's compound of 3 different layers. The first one is the API that exposes the methods to bind names to values. For example, methods to look up or search for these names. Also methods to rename a binding or delete a binding, and so on. Then we have the naming manager that is like the core layer of the architecture that glues everything together. And then we have the JNDI SPI, the service provider interface. And here's where the developers can actually plug different providers. They can actually plug, for example, an LDAP plugin or a DNS or, for example, RMI or Corba. So basically, JNDI will give access to all these naming and directory services through the same common interface, right? So because a code snippet is worth 1,000 words, this is a very simple introduction and example of how to use JNDI. So in the first lines, here we have the configuration of the JNDI context. We are basically saying that we are going to interact with an RMI registry, that is a naming service, where we bind a name to a given Java object. And then that this provider, this RMI registry, is located at the local host at this given port. So then we will be able to initialize the JNDI initial context, and then from that moment on, we can actually bind different names to objects and then recover them using the lookup operation. We can do that from the very same JVM or different JVMs. And as we said before, JNDI is not just for RMI registry. You can actually use any provider type with any provider URL, like for example, in this example, down here, we are using LDAP. So if we want to bind Java objects to a naming service or a directory service, we can use, first of all, like serialization of the Java objects. We're basically serializing the objects and binding the binary representation of the object to the given name that we want to give him. And as a second option, if, for example, the objects that we want to bind are not serializable, or, for example, if the binary representation is too large to fit the naming service, we can also use something that JNDI introduced that is called as naming references. So we have basically two types of naming references. The first one is reference address. That is basically the final address of the object that we want to bind to the naming service. So when we perform the lookup operation, we will receive the JNDI reference. The naming manager will decode this naming reference, will get the address, and then we'll use the address to fetch the final object and return that to the application code. The second type of JNDI reference is a remote factory JNDI reference. In this case, instead of pointing to a remote object, we are basically pointing to a remote factory class that needs to be used to actually instantiate the final object that needs to be returned. So we perform the lookup, we receive the JNDI reference, we extract the factory name, the factory location, we fetch that remote class from the remote location, and then we instantiate that factory in order to generate our object. So when we are talking about loading classes from remote code bases, from remote locations, we are normally expecting some kind of security controls, because otherwise attackers are going to be able to provide a random or arbitrary class with some payload in its constructor or in a static initializer, for example. So we found that within the JNDI stack, the approach to protect this remote class loading is not consistent at all. So in the SPI layer, we have, for example, that for RMI, there is a JVM property that needs to be enabled in order to allow the remote class loading. And this property is normally disabled, is disabled by default. So even if you enable this property, then a security manager will be enforced to be installed to protect where these classes are being loaded from, what kind of code these classes can run, and so on. So for LDAP, it's similar, but we only have the JVM property. There is no security manager enforcement. So once that the developers has enabled this property, the code can actually load remote classes without any security manager enforcement. For Corva, there is a security manager enforcement that is always enforced, but there is no JVM property. And the most interesting part is for the naming manager layer. That, if you remember, is the layer that is going to decode the JNDI references. So it's the one that is going to fetch these remote factory classes that I mentioned. So for the naming manager, there is no JVM property to actually enable or disable. It's always enabled. And there is no security manager enforcement to control where we are loading these remote classes from, and so on. So this is the ideal scenario for an attacker. He can actually provide any class, and there's not going to be any specific control here. So that's the introduction to JNDI, and now we're going to see the two new types of vulnerabilities. The first one being JNDI injection. That is simply an input representation or validation vulnerability where we are, developers are actually taking untrusted data into a JNDI lookup method. And if that's the case, the attackers may be able to gain remote code execution. So the attack process resembles the following. The attacker first needs to bind the payload to the naming or directory service of his choice. And then once that he finds a vulnerable application, he's going to send the exploit that is basically a name that, when looked up, is going to point to his own server, so he can actually return the malicious payload and run and trigger the payload in the server. So we said before that when we initialize a JNDI context, we configure it to work with a given provider type and with a given provider URL. right? So in this case, for example, we are working with RMI registry and with this secure server at this port. So if we perform a lookup, this lookup operation should be resolved in a relatively to this provider type and provider URL. However, this is not true, and the reason is that JNDI implements something that we call internally dynamic protocol switching, and if the attacker is capable of providing an absolute URL, they will be able to override the default provider type and also the default provider URL. So with that, they will be able to point the lookup operation to their own server and then return the JNDI reference to trigger the remote code execution payload. So attackers can actually provide or use different, as we saw before, JNDI can interact with different naming and directory services, like, for example, RMI, LDAP, Corva, and so on. So by providing URLs like the ones on the top of the slide, they can actually point to their own controlled server using RMI, LDAP, Corva, or other protocols. So amongst all the protocols that they can use, we found that 3 of them allow attackers to actually gain remote code execution. The first one is using the remote method invocation, RMI, through the usage of the JNDI references or remote objects that we don't have time to cover during this talk, but is covered in the white paper that will be released later today. Also using Corva, using the interoperable object reference parsing, and also using LDAP through serialized objects, JNDI reference, or remote locations that, again, we don't have time to cover today, but is explained in the white paper. So let's see how we can gain remote code execution using the RMI vector. So basically, the attacker needs to set up his RMI registry and then bind a JNDI reference using a remote factory. So he will be setting like a JNDI reference with any class name and then a factory name and a factory code base that is nothing else than the location of this factory class. So when the actual code in the JDK that gets this JNDI reference and try to decode this reference, they will actually extract the factory class and the factory location from the reference, from the JNDI reference, and then they will be loading this class from this remote location. If you remember, for the naming manager, there is no JVM property to disable this remote class loading, and there is no security manager enforcement. So here, an attacker can actually provide any class, and if there is no security manager, they will succeed on loading this class. And then the class is instantiated. So the attacker that can provide this remote factory, they will be able to put the payload in the constructor or the static initializer. So over to Alex.
Thank you, Alvaro. The detailed information about this click-to-play bypass attack can be found in a blog of Trend Micro, a link you can see on the bottom of our slide. Here we just try to summarize process of this attack. First of all, attacker prepares own web server with some HTML page. This page contains a applet tag with JNLMP files. That files defines initial context as progress class. And when a victim opens this HTML page, a new instance of initial context will be created with properties from our web server. And at the end of its initialization, victim will look up object from our RMI server. RMI server sends JNDI reference, and victim JVM will ask our server to provide factory class. And attacker is able to put any Java code in constructor of this factory class, and it will be executed on a victim's machine. It's a nice example, but it's not only one attack where JNDI lookup trick is used. Other example can be final gadgets for Java deserialization attack. We provided a few already known gadgets. For example, Spring Framework libraries, gadget founded by Zero Thinking. A second one is from RTJAR and used by Matthias Kaiser in his Rhino deserialization chain in OpenJDK 7. We also have found a few interesting gadgets. First one is RMI connection. It's from RTjar2 and very similar to previous one, and setter of statistic service class from Hibernate libraries. As we see, JNDI lookup method can lead to remote code execution. But in previous attacks, an attacker was able to provide code gadget with these lookup calls. What about JNDI injection when untrusted data is directly passed to lookup? We have found examples of this vulnerability in the wild, and we would like to share details about one of them. This vulnerability affects two products, TopLink and EclipseLink. They both are sharing the same core component because Oracle donated source code of TopLink to EclipseLink project. These frameworks handle integration of persistent and object transformation, and it helps developers to stay more focused on their primary tasks and don't care about this integration. One of their key features is RESTful services. It can be very convenient because developer can enable RESTful services just including jar file in lib of his web application, and RESTful services will be exposed automatically. Here we can see how this resource will look. We are interested in the last one, its base operations. This URL will be handled by the next code. In case of post request, call session bin internal method will be called, and JNDI name will be taken from body of our post request. After that, lookup will be called with this JNDI name that is fully controlled by user. Alvaro will show us a demo how possible attack can look.
Okay, so let me switch to the demo. We are going to basically visit a vulnerable application that is a sample application built using JPA, and that is the Java Persistent API, and using the EclipseLink reference implementation. So it's just a sample application to manage contacts. We can add contacts, remove them, and so on. And if we go to the /persistent URL, I don't know if you can see it from the last rows, we can see that we get our response from the RESTful API. So the EclipseLink RESTful APIs are enabled. So we can take this URL and take it to a RESTful client of your choice, or just the command line, whatever you use. And if we check this URL, we have the same result. Now we can actually use this exposed RESTful API to, for example, browse how to add new contacts, how to delete contacts. So everything is automatically handled by this RESTful API that is automatically generated by EclipseLink and TopLink. Now, if we go back to the base operation and use a post request, that is the one that was handled by the code showed by Alex, we just are going to send a JSON request, and here is our injection point. The JNDI name is the one that is going to be resolved by the persistent resource of the RESTful API. So we are going to point it to our own RMI registry, and in our own RMI registry, we are going to bind the Kaboom name to a factory, remote factory JNDI reference. And this remote factory is located in our own controlled HTTP server. So with that, we have everything prepared for the attack. If we go to the victim machine, we see that there is no calculator running. And that's exactly what the factory class is going to do. As soon as we send this payload, the factory class will be retrieved and instantiated. We get some exception about some naming exception. And if we go back to the victim machine, we can see that the payload, the calculator, has been executed, and we have the calculator running in and compromised the server.
Thank you, Alvaro. Fortunately, this vulnerability is fixed yet. It's fixed already, and if you are using TopLink, we highly recommend you to apply the latest July critical patch update of Oracle as soon as possible. If you are using EclipseLink, you need to update your libraries to the latest version as well. We just saw what we can achieve by RMI vector, but in the beginning of our talk we said that is not only one protocol supported in lookup calls. The next our vector is Corba. Java supports 3 types of Corba URLs. We can see them all on our slide. And these URLs can be used to look up objects from Corba server. And Corba server will respond by sending interoperable object reference, or just IOR. It can be in binary format or starts with IOR prefix and string of hex digits. It may contain a lot of information like version, host, port, object key. We are interested in 2 next fields. It's type ID. From this field, Java will take class name of factory and stub classes, and code base. From what location this class will be loaded. So if an attacker specifies own type ID and code base, he will be able to execute own Java code. But Corba vector has own limitation and requirements, and it is not relevant for a default configuration of JVM. It will work only if security manager enabled. Furthermore, this security manager should allow access to our remote code base. We provided a few examples of permission that we can use for that. First one is soccer permission. This line allows to connect to any host, but only to defined ports. It's okay for us. We can start Corba server on any port what we need. File permission. This example allows read access not only on local file system, but on remote location as well. So we can share our folder on our PC, and a target application will try to load classes from there. Uploading feature can be abused as well. Okay, let's imagine that we achieved remote code execution, but our Java code will be limited by security manager because it's loaded from untrusted code base. We are maximalist and wanted to get all permission for our malicious code. So we installed and configured a few application servers from well-known vendors, enabled security manager with default security policy files, and tried to get these all permissions. After a few days of our research, we were able to get this all permission in all our application servers. We have reported all these findings to the vendors, but unfortunately, this issue are not fixed yet, and we are not able to disclose neither names of these application servers nor details how we achieved that. But after our findings, we became more interested in Corba parties and possible attack scenarios with this protocol. So first question was, is it possible to achieve code execution on the Corba server side? Why not? If the server runs with security manager and policy allows us to load load classes from our code base, we will be able to perform the same attack. Furthermore, if you can remember, we already had installed a few application servers. So we quickly test them and figure out that some of them are exposing Corba listeners in default configurations, have needed permission in their policy files. And as we saw a bit earlier, we were able to get all permission for untrusted code. So if a customer enables security manager in this application server, he can automatically open backdoors for remote code execution attack. Other place where we met IOR parser is a read object method of stub classes. As you may know, read object method is one of the entry points for deserialization attacks. So if target application meets mentioned requirements about security manager and its policy, plus attacker is able to provide own data for deserialization, he will not need any additional gadgets. He will be able to achieve remote code execution by using only this one. We have found more than 20 such classes in Oracle JREL libraries and more than 50 in OpenJDK. After our review of libraries from application servers, this number was increased to more than 200. Also, we figured out that JNDI compiler automatically generates this code for client stub classes. So we can expect many such classes in customer libraries. We can give some summary. Core vector can be very dangerous, but only in case if your target has enabled security manager and its policy has some lax permissions.
So we saw that we can use RMI vector or Corva vector to exploit JNDI injection vulnerabilities. Using an LDAP vector is also possible by actually binding a Java object into the LDAP directory and then triggering the execution of the payload during the decoding of these objects. This overlaps with the new vulnerability that we are presenting now, so we are going to skip this vector and explain it when explaining the LDAP entry poisoning. So this is the second vulnerability that we found while researching the JNDI technology. And basically, if an attacker can modify an LDAP entry in an LDAP server or modify the response from an LDAP search, they may be able to execute or gain remote code execution on any vulnerable applications that are actually performing these LDAP searches. So this is a second-order vulnerability. In the first stage, the attacker needs to poison an LDAP entry, and by poisoning we mean that they need to inject or modify some LDAP entry attributes. And once that these LDAP entry or entries are poisoned, any applications that are searching for these poison entries will basically open the door for the attacker to get remote code execution on those vulnerable applications. So we need to understand the difference between a lookup and a search. Basically, lookups are meant for naming services. So we try to get whatever is bound to a name, like an object or a file, for example, but we want to get the object completely. In search operations, those are normally meant for dealing with directory services like LDAP, and we're not interested in receiving an object, but some collection of attributes. Like, for example, you're probably familiar with these LDAP searches where we are using, for example, searching for the user John in the organization unit people and so on. And when we perform the search, we can get all the attributes of the entry or just a bunch of them by controlling which attributes we are interested in. So searches are not getting us Java objects, so there is no remote code execution payload or entry for us. However, there is a special type of search that we call object returning searches, and basically you can provide a search control instance to a search operation. This search control is basically meant to define the scope of the search and what's expected from the search. So this is from the Oracle documentation. It basically says that if the search control contains this set returning object flag set to true, then whatever attributes are received as part of the response, they will be used to reconstruct a Java object. Or if these attributes are not present, then it will basically create a wrapper around these LDAP attributes. So my opinion is even clearer in the code itself. So this is part of the JDK class that handles the search response. And as you can see here, we check for the get returning object flag attribute. And if that's enabled, if that's true, then we will check the attributes in the response for some attributes that are referenced in the Java attributes enumeration. If those attributes are present, then we will proceed with decoding the attributes as a Java object. Otherwise, we will just create the wrapper and return the wrapper. So after auditing like really many applications performing returning object searches, we found that most of them, in not all of them, the developers were actually expecting to get this wrapper. They were not expecting to get any Java objects at all. But because this piece of code is before the wrapper generation, then this will be executed if the Java attributes are present in the response. So these Java attributes are defined in the Java schema that needs to be installed in the LDAP server. It's normally installed or pre-installed in some of them, like Apache DS, for example. They basically define different ways of representing a Java object in a LDAP server. So basically, you can use serialization, you can use JNDI references, you can also use marshaled objects, or remote location. This one is deprecated, but it's still an attack vector because the code is still present in the JDK libraries. So we mentioned that the attacker needs to poison some entry. By poisoning, we basically mean that they need to actually inject some special attributes. So this is a sample entry for John Smith user. And the way that we can poison this entry using Java serialization is by adding this Java serialized data, this Java code base, and this Java class name attributes. So basically in Java serialized data, we can put the payload that is going to get deserialized. And then if this trust URL code base property is enabled in the JVM, that is not normal because it's disabled by default, the attacker will be able to provide his own classes for the deserialization attack, basically located in this Java code base. If this is not enabled, then the attacker can actually proceed with a regular Java deserialization attack and using gadgets from the local class path. But normally attackers won't use this attack vector because using JNDI references is much simple. So to poison an entry and with a JNDI reference, all that the attacker needs to do is add this Java naming reference value to the object class attribute, and then add this Java code base, Java factory, and Java class name. Those are the same one that we defined in the RMI vector. So this is the way that the attackers can actually perform the poisoning of the entries, but how can they actually get the access to compromise or to poison an entry in the first place? So maybe we have like these sample scenarios, probably there are more, but this is, it depends on the attacker, how the attacker, what the level of compromise the attacker has. So for example, rogue employees, if you have a rogue employee in your organization that can access the LDAP server, he will be able to poison any number of entries if he has like credentials for that. But even if you are a regular employee and you are not the LDAP administrator, in many default policies, an employee can actually modify his own attributes instead for a list of blacklisted attributes. So normally you don't want your employees to change their email address or their password without going through the password management tool, but they can modify the home address or even add new attributes. So they can actually use that vector to poison an entry. The second one is vulnerable LDAP server. If your LDAP server is vulnerable to any of the known CVEs for OpenLDAP, Apache DS, Active Directory, then the attacker will be able to compromise the server and use that to poison entries in the server. Also, a different scenario is if you have a vulnerable application that is integrated with LDAP, and the attacker can compromise this application, then they will be able to use the credentials, the LDAP credentials, to proxy pivot into the LDAP server and compromise or poison any number of entries. And we have like more ideas, like for example, most of the modern LDAP servers normally are exposing RESTful API, SOAP web service, DSML gateway, and this is basically just increasing the attack surface for the attackers. So any vulnerabilities on any of these APIs, gateways, or third-party applications that integrate with the LDAP service will be possible for an attacker to use to compromise the server and poison entries. So back to Alex.
According to this attack scenario, we reduced general processes to following two. The first one we can see on this slide. First of all, attackers poisons LDAP entry into LDAP server. After that, he interacts with a target application to force LDAP search, and application sends a LDAP search request to the LDAP server, and this LDAP server returns our poisoned entry. Application tries to decode this entry and will fetch factory class from our server. And after receiving this class, target application will execute Java code from the constructor of factory class. Despite the second scenario is not very likely, it is still possible. For it, an attacker should be able to perform man-in-the-middle attack between target application and LDAP server. So attacker interacts with application to force LDAP search, or just wait for search request from the application. Then he modifies LDAP response and injects own Java attributes in the LDAP response. After that, the next steps are very similar to the previous ones, so we can switch back to Alvaro, and Alvaro will describe an example of such attack and show our next demo.
Thank you. So, because this is a brand new vulnerability, we found like many instances of LDAP entry poisoning in different products, also in LDAP connectors, LDAP libraries, LDAP realms, and so on. We have reported all of them to the corresponding vectors. Most of them are still working on fixing them. Some of them have already fixed them. Some of them have decided to accept the risk. So one of these are Spring Security, and so we are going to show you an example of an LDAP entry poisoning using Spring Security as the example. So Spring Security is a very popular project. Probably all of you know Spring Security. It's used to provide authentication and authorization to Java applications, and more things like security headers and other security controls. And it contains the Spring Security LDAP module that is referenced by more than 1,300 artifacts in Maven Central, so it's really popular, that performs search authentication. And since the version 3.2.0, they are performing this search using this returning object flag set to true, meaning that whatever response they get from the LDAP server, they are going to try to decode those attributes as a Java object, and so the attacker will be able to poison these attributes, authenticate with the user, and then compromise the vulnerable application. So let's see a demo of this attack. So this is a very simple sample application that is using Spring Security for authentication. We can log into this sample application with our user, that is Larry, and then just a dummy application that shows that we are in and nothing else. So we can log out and proceed to poison our entry. We are auto-poisoning our Larry account. So we can use some Python scripts to list the attributes of this Larry account. We can see that it contains the password secret, the UID Larry, and so on. These are the regular attributes. Now we can poison it by adding these special Java attributes. So if we list the attributes after poisoning it, we can see that we have some special new attributes. We have the Java factory. We have also the Java naming reference value for the object class. We have the Java code base, and we have the Java class name. So now the entry is poisoned, and if we just try to log in into we need to start the server that is serving the factory class. If we go back to the victim machine, we can see that there is no calculator running. And now, just by trying to log in, this will force the search of the Larry user. Even with a wrong password, the search will be performed, the result will be decoded as a Java object, and we will be able to compromise any application using Spring Security. Thank you. So with that, we are going to wrap up the presentation. Some brief recommendations. So for developers and operations, do not take untrusted data into any JNDI lookup method or any wrapper around this JNDI lookup method. If you have to do so, sanitize the input and verify that you are not taking absolute URLs that can perform this dynamic protocol switching. Also, if you are writing an integration with LDAP servers, you may want to not use these object returning searches. And if you need to get this LDAP context wrapper, then just get the attributes yourself and then create the wrapper yourself instead of relying on the JDK code for that. So verify and check your JVM properties, maybe your application server JVM properties, and verify that you don't have any remote class loading enabled if that's not necessary for your application, because that's normally something from the past, and if you don't need it, you should be disabling it because attackers can abuse that to make their attacks easier. For an auditor point of view, carefully audit your security manager policy. We found that, as Alex said, we could bypass all of the security manager policies and the default policies that are provided for application servers. We found that they are giving all permissions to too many things, and that can be abused. Also use static analysis tools for finding these vulnerabilities. It's very easy to find them using static analysis, both JNDI injection and LDAP entry poisoning. For pen testers, fast your web applications using these JNDI vectors. Probably RMI is enough, but you want to make sure and try to use the LDAP or the Corva vectors as well. And also, it's a good idea to poison a controlled test account in your LDAP server and try to log into every application that uses LDAP authentication, and probably you will be getting lots and lots of sales coming back from these applications. There are really many applications vulnerable to this attack. And just the main takeaways, audit your application for these two new types of vulnerabilities. Remember that the first slide was that these attackers, these Pwn Storm attackers, were actually using these JNDI tricks against the NATO and White House employees. So they know about these tricks, and probably they know about JNDI injection and LDAP entry poisoning. So just verify that you are not vulnerable to these vulnerabilities. Carefully protect your LDAP servers. Periodically audit your LDAP server and verify that you don't have any entry with Java attributes if you are not using your LDAP server for storing Java objects. That is something that is not very common. And again, if you're using a security manager, make sure that you understand everything you are giving all access or permission to. And with that, thank you very much. If you have any questions, we will be glad to take them. There's a microphone in the aisle. So. Thank you.
Is it on or?
Yes.
Great presentation, thanks. Just one question about what you said. What would be the rationale for Spring to accept the risk? What was their point?
They actually were very responsive during the disclosure of the issue, and they triaged, and we proposed different solutions to fix the issue. At the end of this triage, they decided to not fix the issue and accept the risk. I don't want to speak for them, so we thought that it's fair for the users of Spring Security to know that and decide if they want to accept the risk or not Spring Security. More questions? Okay.
For the LDAP poisoning, right? The sync is in the search like methods, right? So Spring is an example of an app that uses that type of call, which I assume it's just a Java API, right? Mm-hmm.
Yeah. So Spring is basically regarding of what search control you are passing to the search operation. They have a wrapper that in the last minute is just modifying the search control and enabling this returning object flag.
Okay, so have you found an actual call inside the JRE that it's mm-hmm. doing the same, like it's considering this type of attributes and then like actually accepting the attribute with the payload and everything, or it's basically so yeah. The bottom line is like. Is it really like an implementation type of bug where people would need to carefully decide not to trust those attributes, or if they just use a specific method call inside a JRE? Mm-hmm.
So your question was if people should be regular or legitimate users for these attributes?
Yeah, so I mean, like so if you just use a Java API, right, for like search LDAP, like is the attribute considered? Is the attribute that you're using to inject a Java class considered, or it's something that a developer needs to extend?
So if you are just writing an application that is integrating with LDAP server, just don't use this returning object flag. Because the only reason for that is either you want to actually deserialize or decode this Java object, so in that case use it. That's all good. But if you want this LDAP context wrapper, then don't use this returning object flag to generate this wrapper for you. Just get the attributes and use the attributes to create your own wrapper.
Okay.
So I don't know if that answers the question.
That answer. Yes. Okay.
Perfect. One more question?
Yeah, question about the JNDI injection. If the authentication is enabled, I'm thinking about the use case for if Glassfish or GBus has the IOP port open. If authentication is enabled, are you able to do some lookup prior authentication, or this will block all the risk?
You are talking about the Eclipse link and top link? Or in general?
I don't remember if it's RMI or Corba protocol, but some container have the port open to do lookups. And
you mean the
Corba,
IOP, the Corba listeners?
yeah, the first part of the
So,
talk.
as we said on our presentation, you need to have enabled security manager and you need to have access to your remote code or local code. You need to upload file there. And if your security manager enabled, this vector is open.
Okay, so even if authentication is enabled?
If authentication enabled in Corba listeners,
Yeah.
We cannot answer on this question because we have not tested that configuration.
Okay, thanks.
Thank you. One more question.
Hi, a really good talk. Two questions. One, did you notice any difference between LDAP servers such as Microsoft Active Directory?
Can you get closer to them?
Did you notice any differences with Microsoft Active Directory versus like a open LDAP server when exploiting this type of bug?
In this case, both of them don't have the Java schema pre-installed by default. So if the attacker can actually compromise the LDAP server through a vulnerability or because they have administrator credentials, they can install the Java schema. Otherwise, both of them don't have this Java schema, so the attacker, when trying to poison an issue, an entry, won't be successful. But normally, if the attacker can poison an entry, then they can install the schema. So other LDAP servers like Apache DS and some others come with the with the Java schema pre-installed. But there is no difference between Active Directory or LDAP, Open LDAP or any.
Gotcha. Okay, cool. Second question is about fuzzing for black box testing, for when you're doing pen testing. You said use a fuzzer to determine if this was vulnerable.
Well, yeah, sorry, go ahead.
So how would, like, if you didn't know that the LDAP record had those properties in there, like, what type of fuzzing were you doing if you did not have access to the code?
Okay, that's a good question, but if you are using like a scanner, like, I don't know, Burp or Web Inspect,
sure.
You normally will get the parameters that the application is accepting, and then based on the name, you may have an idea that it's taking a JNDI name or something like repo or like something like data source. Those are candidates for testing against a JNDI injection. So probably JNDI injection is not like the new SQL injection is not going to be all over the place, but we think that it's going to be present in many enterprise level applications because JNDI is used there all over the place.
Cool. Thank you.
Okay. We don't have time for more questions. Okay. Any question? Last one? Okay, so thank you very much.